the pigeonhole principle, right? Let's just have a look at it, because we sort of started unpacking it last lesson. And a lot of you guys were asking, oh, my favorite question, when are we going to use this? You know, it can be used to impress your friends by solving interesting riddles, but I actually did find an interesting application of this one. When you are looking at computers, right, one thing that we're concerned about is file sizes. We want to make these files as small as possible. And there are ways we can compress those, right? Has anyone seen those before? Zip files is one thing, RAR files another time. We can make things smaller, and that kind of intrigued me, because it was like, you know, if we have this movie, how can I just make it smaller, right, without losing anything? Like, why wouldn't you just do that in the first place? The idea comes from something like this. If you take this kind of diagram, I have 2 black boxes and 3 blue boxes. There's another way you can express this, right? In a much more compressed way. I could just write it like this. 2 black and 2 blue. Right? You can see that's actually like, you know, half the size. 3 blue, thanks. It's like half the size, right? Or less than half the size. And that's the basic idea of compression, right? We represent information in another way, but still having the same message. The pigeonhole principle gives us a limit to that, because at a certain point, right, we can only compress things so much. And sort of like assigning things to different things, okay, it tells us that there's a limit to the compression that we can actually do. But when we're looking at the problems that we're trying to solve, we get a whole variety of questions that are asked. We're often asked to actually justify our answer. Okay, we need to justify your answer. I'll talk a bit about how we can do that. But sometimes we need to find things as well. Sometimes we need to find n. What does n represent in our pigeonhole principle? The number of pigeons. And often they'll ask you to find the least number of pigeons that satisfies this, right? So sometimes you want to find the pigeons, and you want to find, you know, the minimum of them. Okay, that helps you satisfy the condition. The other thing that you'll asked to find often is finding n over k. What's n over k?
It's like one of them has to have at least that many.
Right. And it's pretty hard to express with words, right? But if you think back to your pigeonhole principle, right, and you have this one extra guy here, right, they need to contain at least 5 divided by 4 pigeons, right? They need to contain at least that many. Maybe you can say that's, you know, at least how many in each hole, right? The other thing that I sort of didn't touch on last lesson was that, hang on, if I take this one, right, 5 pigeons and 4 holes, when you do that, n over k, what's that actually equal to? 1 point, what is that, 2.5? Yeah. If you're thinking about n pigeons, right, the objects that we're dealing with, it's not possible to have 1.25, you know, pigeons, right? But let's say you need to have at least that many. So anytime you evaluate this and you get a decimal, we need to round that answer up to the nearest whole number, okay, effectively, right? So anytime you're looking at finding n over k and you're calculating that, if you do get a decimal, you always round up, okay, because that's like the kind of flaw. It has to be at least this amount. We always have to round up in that situation. I want to talk about a proof now, right? What does a proof involve? In this particular concept, a proof, we often actually want to use words. We want to use English here. Where English and maths collide. We want to use English. And sometimes, right, and again, you have the freedom here, right? A proof should convince me that you know this idea through and through. Not only sometimes you want to use English, but sometimes you want to identify the pigeons and pigeonholes. You want to identify the pigeons and pigeonholes. And kind of like English with an essay, you have the freedom, right? Sometimes it's more appropriate to use one method or the other, but as long as you're convincing me or the marker, then that's fine. Can you get those down for me? So these are the conditions of how we can approach pigeonhole principle. Questions are these types of questions here, and a proof needs to use these things here. All right. So let's look at a show that question. How do we actually use English in a mathematics subject, right? We want to show that for 36 pigeons randomly assigned to 10 pigeonholes, there is at least one with at least 4 pigeons. Okay, so a few things going on here. The thing is, they've already given me the answer here, so I know that I have to show this, right? There's no point just restating the question. They've already given the answer here. So I have to show that I understand why 36 results in at least one of the holes being assigned with at least 4. Again, one thing that I was wrapping my head around is, hang on, like, can't I just assign 36 to one of these here? Like, if I just chuck them all in the first one, then there's at least 4 there, right? Okay, but remember, this idea, we want to show that we know that 36 guarantees this. It's not just off by chance of how we assign them, this guarantees the situation. The way I do that is I think about the worst possible scenario, right? What's the worst possible scenario? If you think about it, right, if you spread all of these out, right, if you spread all of these out so that there's 3 of them in each of these, how many pigeons is that? 30. So here's what I'm going to say. I'm not only going to show them why 36 is an answer, I want to show them why 30 is not an answer. Because this is to show that I understand what's actually going on here. It is possible that with 30 pigeons, there are 3 in each. It's possible that with 30 pigeons, there are 3 in each. But any additional pigeon, what's going to happen after that? All right. Well, it won't be 4 in each, but it will mean, at least one of them will have at least 4. Can you see that? Right? And that's what we looked at. That is the pigeonhole principle, right? So any additional one will ensure there is at least one hole with at least 4.
So, is the answer like both lines, like the black bit as well?
So that's the question. Sorry. Yeah, yeah. And what is that? Well, that's 30 plus 1, which equals to 31, right? And it may seem kind of obvious that this is something, but you have to think about in the reference to what this question is asking. They're giving you the answer. So you have to prove without any doubt that you know what's actually happening here. Have we answered the question, do you reckon? Yeah. Are we convinced?
I'm pretty convinced.
You're pretty convinced?
Are you going to say it's not?
Well, we haven't, like, what's the question actually asking though? Show for how many pigeons? 36, right? Yeah, well, since you could just easily say, right, and there's a few ways you could do this, but I could just say, since 36, I don't know why I'm using a different color now. Since 36 is more than 31, there's at least 4 in one of the holes. Yeah, you can do that. So it saves you some spaces. It's even worse than that, right? Because now we've got like some sentence structure. We've got like an introduction, we've got a body, and we don't have quotes, but I've got a justification here. I've got like a calculation, which is reinforcing this, right? Yeah, that'd be cool. Yeah. Yeah.